Okay, so welcome you all for today's session of our quantum mechanics lecture series. So today we are going to continue whatever we started in the last lecture, which is about eigenvectors and eigenfunctions, and more importantly, eigenfunction expansions. I think what's going to be so these are like three important central pieces of when we do quantum physics. So we first two we call them eigenspectrum, and then it's not just eigenspectrum which is important. I think equally important is something called eigenfunction expansion. Okay, so I think someone is not on mute. Can you mute yourself? So there's a bit of a background noise. So okay, so what we discussed last time, I think what we the main message from the last lecture was that eigen spectrum. So when we solve these quantum mechanics is the central problem which we solve. The main kind of a central theme of quantum mechanics is about solving eigenvalue equations, and therefore we got into some depths of understanding what eigenvalue problems are, not only from a formal and mathematical point of view, but also from a physics point of view. That why is it that what is the physical reason that eigenvalue problems are important? And what we understood is that not only at a quantum mechanics level, but also classically when we deal with problems like theory of vibrations, oscillations, and waves, and essentially whenever we solve these differential equations, which are equations of motion even of classical systems, these problems are also eigenvalue problems. So we demonstrated this by taking an example from classical vibrations. We understood we took a mass spring system which was a with 2 degrees of freedom. It was a coupled mass spring system which had two masses which were coupled to each other. And then we understood that whenever you have such, and it's a prototypical what we call as many body system. It's a prototypical many body system, though it had only it's kind of a two body problem. However, it has some essentials of many body physics at a classical level. Okay, and what we understood is that the eigenfunctions and eigenspectra has something to do. It has always something to do with something called the normal modes. Okay, and so the normal modes is what we are interested in from a physics point of view, and it's the normal modes which describe the physics of that many body system. I gave from a quantum point of view, from a quantum many body physics point of view, I gave or even from a quantum mechanics point of view, I gave some examples, like as if we examples of the normal modes are like phonons, photons, and because these are the particles which we are aware of, but we typically do not associate them with normal modes. Okay, however, at they are all of them are normal modes often, and there's associated eigenvalue problem with phonons, with photons, and other particles as well. Okay, so so quantum mechanics, so when we solve the eigenvalue problem in quantum mechanics, physically what we are doing is we are trying to calculate the normal modes of that physical system. Okay, so when we have just one quantum harmonic oscillator, it's simple harmonic oscillator, the normal modes and functions of that eigenfunction normal modes are anyway same, but we don't get a flavor of eigen normal modes which typically describe a collective, it's a collective oscillation or it's a collective behavior of a system. But when you have a single oscillator, even if you have a quantum oscillator, it doesn't look like we are talking about normal modes, but nevertheless the eigenfunctions describe the normal modes of that quantum system. Okay, so this also reminds me of a quote about physical systems, that it has been said that the physical systems are divided in two categories. One is one class is the oscillators. Let's also call the harmonic oscillators. So in the physical systems which we study are mostly harmonic is just kind of an uh, to mention that it's a second order which is important. So and then we have also we call them spin systems. So whole of physical systems can be in some sense described or categorized into two main categories. One is the oscillators, and the oscillators is which describes the so-called bosonic world. Okay, so all the bosonic world can be understood as harmonic oscillators. Then we have spin systems, which is basically refers to the fermionic world, because fermions always have a very interesting spin properties. They have spin half integral spins, like as one half or maybe more associated with them. So they have half integral spin properties, and those spin properties make them very, very interesting. So the whole quantum world can be, in terms of the entities you deal with, can be divided into bosonic world and the fermionic world. And what last time is entirely in terms of at the level of the harmonic oscillators. But similarly, whatever we have done for the bosonic harmonic oscillators, a fermionic system itself can be understood from an oscillator point of view, though the degrees of freedom will be different. There's essential difference between bosons and fermions. However, from a equation point of view, from calculating, doing the eigenvalue equation for fermions also, so we have a similar kind of a structure for fermions also. Like as we have creation and annihilation operators for bosons, similarly we have creation and annihilation operators and number operators associated with the fermions also. So that way we can always write down Hamiltonian, fermionic Hamiltonians also as some sort of oscillators. That way, so oscillators are important because that gives us a very transparent and a clear example of understanding what are the eigenfunctions, what are the normal modes, what are the eigenfunctions, what are the eigenvectors, fine, and what are the eigenvalues and how they are important. So I think to understand the crux of eigenvalue problem in quantum mechanics, as I said last time also, oscillator is the best example to understand the more details of what these eigenfunctions and the significance of these, physical significance of these eigenvalues and eigenfunctions is in physics. Okay, so now today what we will do, we will take it forward. I mean, I think assuming that we have got a good grasp and intuitive hold on what these functions and numbers are, so we want to take it forward and have a more discussion in the context of quantum mechanics. Okay, in the quantum mechanics, so last time the general discussion was in terms of the eigenspectrum of general linear operators, but today we'll make ourselves restrictive about some particular class of operators. And in quantum mechanics, it so happens, first of all, quantum mechanics, as we know, the state space from a mathematical point of view is basically a complex vector space. Okay, so we always have that our space, let me call it right, Vn of C, which basically means we still have we have a vector space whose dimension is n, where n can be very large. In many systems, it is infinite. So we have a vector space, but it is with a complex number of fields. So it's a complex vector space. So we have the numbers which we use in for representing various quantities are complex numbers. So that's what Vn of C is. So therefore, the operators which will act on this space, so we can have a general class of linear operators, but all of them will not correspond to the physical system. Therefore, there is a special class of operators which are called Hermitian operators. Okay, and we will get into the details of, we will try to understand and ask the question, why is it that we need Hermitian operators in quantum mechanics? Okay, we'll get a physical insight into that, but we will be essentially asking ourselves the question. Let's say now I want, because my so-called observables in quantum mechanics are represented by Hermitian operators. So therefore, I am interested in solving the eigenvalue problem, not only for general operators, but eigenvalue problem for Hermitian operators. So that is the kind of a problem we are interested in. We want to solve the eigenvalue problem of Hermitian operators. Okay, and therefore, so first things first. So first we'll ask the question, what is a Hermitian operator, or the mathematical property, let me call it Hermiticity. What is the Hermiticity of an operator? Okay, and I hope we are all familiar where the name Hermitian or the Hermiticity comes. It comes from a mathematician whose name is Charles Hermite, who has done a lot of work in analysis, and there are differential equations after his name. So so before we go on defining a Hermitian operator, there is something called let me remind you of an earlier discussion which we had. We talked about, when we talk about complex vector spaces, or in general any vector space, we always have a notion of a dual vector space. Okay, so and without dual vector space, we discussed that it is not possible to take inner products. So whenever we take inner products, unless and until the vector space is real, okay, like a Euclidean vector space, which is dual of itself. So in all in other cases, we need to have a dual vector space. So what is the dual vector space in quantum mechanics? In quantum mechanics, we have these ket vectors. Say they belong based on complex number C, and then corresponding to each vector, there is another vector which belongs to another, not to the same space but to the dual space. Okay, on the same number field. Okay, now the question is, and these are important, we realized earlier on, we need to have both these vector spaces there for doing physics. Why is it that at that time we realized that whenever we take inner product, we of any arbitrary functions, arbitrary wave functions, it's always the case that this guy comes from a vector space Vn, while as this fellow over here comes from its dual Vn conjugate, let me call it. Okay, so even talking about the questions of overlap between two wave functions, or questions like orthogonality, or even questions like a norm of a wave function, so we will have to use these dual vector spaces. But today what we are interested in is, like, we understand when we have operators, let's say we have operators vector acting on ket vectors, the main vector space. Let's say I have an operator L, it acts on ket psi, and we know it gets transformed to another ket. Okay, it may be belonging to a different vector space, but it still is a ket vector space. So let's call it ket space. So this is a ket space, and then it also gets mapped to another vector in the ket space. Okay, so that's what's happening. Now the question which we are asking is that what happens, let's say what kind of operator, so let's say we have some question mark here, what kind of operator is going to act on the bra vector? Let me put it here. So if I have a bra vector psi, so what kind of operator is going to act on that operator, and how is that operator? So let's first of all call it just L prime. There is going to be an operator which is going to act on, I'm sorry. So there's going to be an operator L prime which is going to act on this bra vector, and then we would like to identify what is going to be its action on this bra vector, plus what's going to be its relation with our original vector operator which acts on the ket space. Okay, so these are the questions which we want to ask, and that's why the question of a notion of an adjoint of an operator becomes important. Okay, so when we have an operator L which acts on ket operator, which acts on ket psi, then corresponding to it, the way we had psi, and correspondingly we had a bra state of it. So this is a ket state, this is a bra state corresponding. Similarly, when we have an operator L acting on here, correspondingly we have an operator L adjoint acting on over here. So there is an operator. So this operator L cannot act on psi. This is to be noticed. L itself cannot act on psi space. It cannot act on the dual space, because L is an operator. L is a linear operator, whose action is defined with respect to the ket space. So it's a linear transformation which acts on ket space only. So which means, let's say it's a rotation, so then it is going to rotate only the ket vectors, while as the bra vectors, we know that belongs to a different space. And whenever you define linear transformations are defined with respect to a vector space. Let's say you have a vector space, and it acts on a vector which is in a vector space. Okay, so therefore, because dual vector space belongs to a different space, so we will have to have a different set of operators which are acting on that space. Okay, so what are those operators? We just call them adjoint operators. So what is an adjoint? And now what's an adjoint of an operator? Adjoint of an operator is an operator which acts on the bra vector, the bra vector itself being the dual of the psi. Okay, let me say it this way. So we have psi, and then we have a dual of psi. Therefore, there's an operator L, and L dagger is going to be the adjoint of the L. Okay, so L dagger is so-called adjoint operator, adjoint of L operator. Okay, so L always acts on psi space. Okay, and correspondingly L dagger always acts on the Brauss space. So L is for ket space. Let's make it clear. It acts only on ket space. Its definition is with respect to the ket space, where L dagger is always, it acts only on the Brauss space. This is why is it that we have to have a two set of operators? It tells you that these two vector spaces, even though they are dual to each other, they are different from each other. They're very different from each other to such an extent that you need to have a different set of operators which are going to act on them. Okay, now what's mathematically what's going on over here. But before I give you a mathematical definition of what an adjoint is, I want to give a physical flavor of what is going on. What is the physical meaning of the adjointness of an operator? Fine. So you cannot get it because most of the operators which we are dealing with, they are all already Hermitian. Let's say we deal with rotation matrices, so all of them are Hermitian. So in them Hermitian operators, it's very difficult to understand the distinction between an adjoint and the operator itself. Therefore, let's take an different kind of an example where adjoint is different. So adjoint has something to do, it's very similar operation like as we do complex conjugation. Okay, and I want to remind you that complex conjugation is an antilinear operation. Okay, so and adjoint has something to do with complex conjugation. And why is complex conjugation, any form of complex conjugation, important in physics? Because one example is let's say you want to represent how do you represent the fact that you have the wave function which you associate with two particles, two charged particles. One of them is positively charged, let's call it psi positive, and another is negatively charged. Okay, how do we go from, because it's only the charge, one quantum number which is different from the another. It's like only the change of the sign when you go from one wave function to the another wave function. So how do you get that? How do you get that change of sign? So this change of sign, without getting too much into details, has something to do with the complex conjugation. Okay, so the way you can understand it is that maybe the charge itself will be somehow lying, it will be somewhere over here. It will be some charge operator, let's say, and that eigenvalue is going to give us a charge, the value of the charge. And but the way if we take a complex conjugation of this guy, it's going to give me minus. So if I represent charge or the charge operator in such a manner, it's an exponential operator of this sort, then if I take in conjugation of that operator, it's going to give me minus sign. That's going to give me the reversal. That's the reversal. So there are many such reversals which happen. And it is, so now what is happening is here is let's say positive. Let's say we represent our charges on a line. Let's say we start from 0. So and my charge plus E is coming over here, and charge minus E is coming over here on the number line. Okay, so there's some sort of a direction, at least in charge is a scalar, so there is no any significance for the direction. But because they lie on two different points on the axes, so charge this is on one direction, so there is a directionality, so it's happening on this direction, and this is happening in another direction. This is lying on another side of the axis. Okay, so these are two different directions. So this is the one simple example of why adjointness is important. Adjointness refers to two different directions, but wait a moment, I am going to give you a better example of where what adjointness has to do with the direction. So adjointness, let us say an event is happening and we have a particle. Let me give you now a better example. Let's say we have a particle which is moving say in this direction. I'll just, though we can do it in Feynman diagrams, but let me make it very simple. So we have a particle which is going in this direction. The particle has an energy momentum k, and let's say spin k, k sigma. Okay, this is the state of this particle. Then there is going to be, let's say we have a another particle which is an antiparticle of this guy. So it may have antiparticle, let's say for a moment, for our sake of our discussion, though its momentum is also going to be different, but for the sake of our discussion, we're going to say that it is momentum is let's say k minus times k, and then it is spin is going to remain same. So these are like as two particles which are related to each other in the way they are antiparticles of each other. That way, the way we assume, the way they appear in the Feynman diagrams, or the way you can understand them, how they are moving, the way you write down Feynman diagrams for them, is you write in one direction. Let's say if a particle is moving in one direction, its antiparticle is moving in another direction. How are particle and antiparticle, how are they related with each other? They are adjoint. If you write their wave functions or even operators later on, so they are adjoints of each other. Okay, so what an adjoint is, and why is it, this looks very, the distinction is very clear here, because in this case, these adjoints are not same. Like as the operators by which we represent them, they are antilinear operators. Like as when you do a time reversal symmetry, when you do charge conjugation symmetry, or any other forms of symmetries, CPT symmetries, all of them are antilinear. And in case of antilinear operators, the distinction between adjoint and the actual state is very, very different, is very distinct. Okay, therefore the adjointness basically means, let's say if we have a particle going in one direction, its adjoint is another particle, or we call it antiparticle, going in totally opposite direction. Okay, so that is how different they are, and they are two different states. Similarly, we can have in phenomena where we have spin important, so adjointness will mean, let's say we have a spin particle which is going from, we have a spin half particle which is going from this state, and it's going to another state. So this is a state, actual state, and let's say there's a transition, spin transition happening, it's going over here. So this will be a one direction represented by one a function, state vector. Then its adjoint process will be like this. Adjoint process will take us back. So adjoint process will be like this is a spin down, it comes back. So that spin is more or less, there's some sort of a conservation in the spin. Okay, so this process, as a Feynman, you can also think of it as a Feynman diagram. So there's a process which is in the forward direction, then the adjoint is another process which goes in the reverse direction. So that is why we have adjoints, which are really, really important in physics. What they represent are two different directions. When I say direction, it does not specifically physically mean direction only. It means there's a process which is a one flow, and then there's another process which is an opposite flow in opposite direction. Like which happens in many times, if you look at these Feynman or scattering diagrams, you can see the flow. The momentum is one direction, then spin is in one direction, or you have helicity in one direction. So that kind of stuff is happening. Then adjoint will always mean a process which is in opposite direction. Okay, so that is why we have these adjoints important. Similarly, you can have, I think the charge conjugation gives us a sense of, because charge conjugation is in some sense a generalization of complex conjugation, because charge conjugation is also an antilinear operation, just that it is represented by not just a simple conjugate operator there. There's an operator for complex conjugation. Okay, however, these are the examples of what an adjoint is and why. So adjoint is a physical, there's a physical process associated with the adjoint. That's why, because every linear operator, every Hermitian operator represents a process. Okay, and then there's an opposite, an adjoint operator of that will represent the opposite process of that. Okay, so I think that is what an adjoint is. And now mathematically, how do we, you will see in mathematically also, when we write down the operator, you will see some sense of whatever I have just said, it will become clear to you. So mathematically, how do we write? So let's say we have an operator L, okay, and it's acting on state, let's say V, okay, and to see the effect of it, let's also multiply it with another draw from this side. Let's sandwich L between U and V, okay, and this is our actual operator. So we can also, this whatever I have written here, later on I will write it in terms of the I will call them U and V here, or later on I will call them also Lij. Lij are the matrix elements of our operator. Okay, now what is going to be the effect of what is going to be the adjoint operator now? So let's take a look. First of all, we should understand, I think I have already written it. Let me write it down here. L acts on psi state, while as it's the adjoint operator which acts on the bra state. Fine, this part is clear to us. So now let me do it this way. So I can write down this thing from here. I can go here. So I can write, I hope you agree with me. So now if I have to write down my adjoint operator, let me see what's the adjoint operator. So I'll write U, then I will write adjoint operator, then I will write V. Okay, let's see what's going on. So now this L adjoint will not act on V, it will act on the U, bra. Okay, so I can also write it, we can also write down this way. Okay, then we will have V. Okay, what does this guy mean? Let's expand it. So this guy always means, first let me say, if I have a number lambda, it's getting, if I have a number lambda which multiplies a vector, bra vector u, so I can always write down it lambda conjugate u. I'm sorry, the bra u. Okay, I hope this is clear to you guys. We have already talked about the antilinearity of the bra space. Okay, similarly, if we have an operator L acting on u, it can be always written down written as bra u adjoint L operator. Okay, so because I think this is very clear that it's the adjoints which act on the bra space. There cannot be other vectors, and this is just compared to bracket notation of writing down these adjoint operators. So that's what I have written. That's this notation I have used it here. Okay, so which means that L, U, and V are here. Now what we can do is that here one kind of a simple way of doing a bit of an operation here is to understand that Lu is itself another kind of a vector. Let's say, because when L acts on U, it will become another dual vector. Let's call it U prime. Okay. Okay. And if we use that property that this is a U prime and this is V, we can always use the properties of the scalar product. And in scalar product, we know that if you just reverse the directions of the operators, they always get conjugated. Okay. So what basically it means is, if you had earlier you started with a U state, okay, and if you change that, if you reverse that state, you had U state here, you wanted to convert it into the ket, it will always get conjugated. Conjugation means there's a bra, so that's a dual of it. Conjugation is just to say that it is a, you cannot just take any ket state and just convert it into the bra. That does not work, because the operations on the bra space are antilinear. So when you take any ket and change it into bra, or you take any bra and change it into ket, you have to always complex conjugate that vector. Fine. So that's what we have done. That's what we are going to do here. So this is what I have done. I have reversed the things. I have changed the ket into bra, and then Lu, which you can think of it as a U prime, that I have changed it into ket. And by doing that, I have basically I had to conjugate it. So let me make it simple for you. Let's say I have phi and psi. So phi psi, if you want to change it, the order, so it will always be equal to this thing. This is what I have done. This is what I mean. Okay. So in case of this is what happens when you especially do with when psi and phi are complex, they are the complex functions, or they are the vectors based on complex vector space, then you have to always do this operation, right? Because why this operation is needed? Because the scalar product is linear. It's linear in psi, but it is antilinear in phi, which is what that means. Is that means something like this, that if you take your lambda outside your bra, it's always, actually it looks lambda inside the bra, but actually it's not lambda, it's lambda conjugate. It's a lambda conjugate. So it is the lambda conjugates which are getting multiplied to the bra vectors. So these are the properties, and it has everything to do with the antilinear nature of the bra space. Okay, so if we use this one, so this is what we have. So then, and why do we do it? Because we want to compare our adjoint vector with our original vector. Okay, or I'm sorry, our adjoint operator with the original operator. So then in that sense, what we have got L conjugate. Okay, so now it looks, now let's bring another original one. What we had earlier U, then L, then V. Now we can compare it. Now let's look at two things. So this was our original operator. It was acting on V, and it was getting multiplied with the bra vector U. Okay, the adjoint can be similarly thought of. What's the adjoint operator? Because this is, we have got it from here. So the adjoint operator L dagger can be thought of as an operator, the actual operator, like as we had here. This kind of an operator, with this difference that it is not acting on V, it's rather acting on U. Okay, then it's getting multiplied by V, then it's getting conjugated also. Whatever the result we get, that also gets conjugated. So there are two operations which are happening. So one thing which has happened is that there has been a transposition that has happened between V and U. So a transposition has happened, and then followed by conjugation. Okay, so that's what adjoint is. Adjoint is two operations. Okay, one is the transposition of it. That's what you would have learned in matrix algebra, that adjoint is basically transposition and conjugation, and that's what's happening here also. That you have, if you in this bracket notation also, this is what we observe, that the adjoint operator is an operator which acts on, let's say initially your operator was acting on V, the adjoint acts on the U. This is to be noted, and this is always like that, because adjoints will always act on the Browse space, and then it gets multiplied by V, then there's a complex conjugation. Okay, this is what an adjoint is. So given an operator L, its adjoint has this effect. So if I write it in a kind of a matrix elements language, so I'll just make this slide change in the notation. So if I had now I and then L, then J, what adjoint basically is doing, so adjoint operator L operator will be, so it will be J, L, and I, then complex conjugation. So this is the this looks like L, but this is the L adjoint actually. So our original operator was Lij. The adjoint operator is Lji conjugate. So this is the adjoint operator. So given an operator whose matrix element is Lij, the matrix elements of its adjoint operator are Lji conjugate. So that's what an adjoint operator is. So you can see that there's a reversal, which I was earlier talking about, that adjoint operators always have something to do with a reversal. Like as if you have a particle going in one direction, there's a reversal of that momentum direction. You can see it reversal happening here. Let's say there was a process, we had an initial state I and we have a final state J, because this is a matrix element. Matrix element means it's a transition element between two states, initial state I and final state J. Okay, so what is happening is that in case of adjoint, what's happening is that you have that process reversed. If the particle was going from one state I to J, the adjoint operation basically takes it from J to I. Okay, and I think why they are important, why now Hermitian operators are important, because in the Hermitian operator, these processes close, and that's why there's conservation. Like as if we had only these operators, we have the operators which are not self-Hermitian, which are not self-adjoint, they will be doing transition in one direction. They will not be closing the loop. They will not be like a starting from ith state, doing a transition and taking the state back to the original state. They will not be able to do that. But that's what in physical phenomena happens. Like an electron hops from one side, goes to another side, then it comes back. That's what happens in a solid is. Like as that's what kinetic energy does. With the kinetic energy, electron hops from one side to the another side, but then it also comes back. It does not remain in another side. Okay, so because we have to take care of the conservation of the energy. So that's why we have these Hermitian operators. Now, what are the Hermitian operators? Hermitian operators are those operators in which the reversal is basically same, which means the Hermitian operators can take a particle from one state to another state, then they can also bring it back. This is really, really important. The Hermitian operators are those operators which will take a particle or any quantum system from one state to another state, then also bring it back to the original state. Okay, so I think that is that's what is the important property of a Hermitian operator, that they are their own adjoints. They are their own adjoints. Okay, and I think you would some of you would have heard of the examples where the particles are their own antiparticles, which that itself has something to do with complex charge conjugation. So the particles which are their own antiparticles, it means for them complex conjugation has no effect. Complex conjugation has eigenvalue in some sense 1. It does not do anything. Okay, so whatever the complex conjugation typically takes you from particle to antiparticle, but in case of neutral particles, it takes you to the particle itself. Similarly, the Hermitian operator is a similar example, which does not take you to a different kind of a state. It takes you to some different state, but it also brings you back. That is what a Hermitian operator is. So in our language, so Hermitian operator is a operator such that Lji conjugate is equal to same. So in terms of the matrix elements, this is same, or if I write it in the bracket notation, basically we are saying it is an operator such that it acts on V. Okay, doesn't matter, it will be acting on Lu and Lu and V. Okay, so that is if you have any such operator, that's called a Hermitian operator. Okay, but physically, what does it mean? Hermitian operator physically means that it has the Hermitian operator can be divided into two parts. One is the original part, let's take it the base part, and then there's the adjoint part, such that together, both of them together make the whole operator. But they, what they do is that they the first part does the first part of the process. It takes particle to one in one direction, that the adjoint part brings it back together. They always close the loop. They do not keep they don't go in only one direction, what an adjoint will do. If you have an operator which is not self Hermitian, it will take energy, momentum, spin in only one direction. It will not bring them back. So I think that's the sense of what these Hermitian operators are doing. And you would see what is that complex conjugation doing over there. I will come to that shortly. Okay, so this is what a definition of Hermitian operator is, and it has a strong physical. This definition, I am just trying to motivate why there are Hermitian operators. There is not a mathematical reason behind that, rather there's a physical reason. That because quantum processes are closed processes. If you are describing a quantum system, it's a closed system. It's not that energy will go always in one direction. So it is not that momentum will always keep on moving out of the system or inside the system. It's not possible. So hermeticity in some sense refers to that closedness of your quantum system, that if your energy is taking, it's going from one direction to another, make sure that it comes back to the original place. Okay, or it also means, like, say, if you have a particle, if we just have this, I think hermeticity can be understood in a very nice manner in some sort of a Feynman diagram. So let's say we have a particle number 1 with momentum k1, and let's say just k1, and let's say some spin 1, and this is in that state. And then we have a particle with k2 and sigma 2. Okay, so in that state they come together, and then they get annihilated in terms of a photon. This is a kind of a photon. Okay, so but it has to, the hermeticity makes sure that whatever, so if there was some energy here, there was some energy over here, whatever you get here, you get a particle in the state k and sigma. So it's very, very important that that the energies, the momenta, they add up correctly, and the spin is add up correctly. And then if you think of a backward process, that backward process also adds up in a correct fashion. So that is in some sense what the hermeticity refers to, because hermeticity refers to these quantum processes, and the fact that there's a flow of the momentum flow, spin transition is happening. So you have to make sure that they remain physical. You cannot just do arbitrary things with these physical processes. That is not allowed in physics. And hermeticity is a very strict condition in quantum mechanics, to take a very strict care of the fact that these things are taken into consideration. Okay, I think that is why hermeticity is an essential and a very essential condition in quantum mechanics. Okay, and then plus there's a related, it's not a separate condition, which is called a unitarity. Unitarity and hermeticity are very much related to each other. So unitarity, you would have been hearing a lot about unitary when you talk about in news. There's been recently a news about black hole information paradox. So we talk about unitarity. Unitarity refers to a similar thing. It talks about, like, as if your probabilities in quantum systems, the probabilities will remain conserved. Okay, or if you have a norm of a vector, it should not change. That's what unitarity makes sure. But unitarity itself is related to the Hermitian operators, because every unitary operator is written as an exponential of a Hermitian operator. So in that sense, in a mathematical way, the hermeticity also leads to the unitarity of the quantum theory, quantum physics. Okay, so unitarity and hermeticity being related to each other are a very essential aspect of quantum physics. And it's only when you go to the open quantum systems, when you relax, then you have to relax these conditions. Then you say, okay, we don't need a Hermitian operator. But in every closed quantum system, you have to make sure that there is your observables are represented by Hermitian operators. Now, so far so good. It was just the definition and the motivation of what a Hermitian operator is and why do we need them. Okay, because typically if someone asks you why do we need Hermitian operators, they will give you a very quick and incomplete answer that Hermitian operators, we have observables in quantum mechanics as Hermitian operators because their eigenvalues are real. Okay, which is true, which is very true. That's why that conjugate, that's why realness has something to do with this conjugate thing here. Okay, that's why that conjugation is there. But that's only one part of it. But there's a reversal part of it, transposition part of it also happening. Okay, and we are saying that there are two things which are same. One, even if you complex conjugate that operator, it still remains same. or in other words, if you have to keep the system, Hermitian operator is a system or operator such that you do two things together, that you take complex conjugation and you also take transposition, then it should remain the same. It's not only the real part of it that is important in a Hermitian operator. The reversal part is equally important. Okay, so in fact together together transposition plus conjugation together define the adjointness of an operator, of a Hermitian operator. Okay, so therefore they are important as when you look at it from a physical process or quantum processes point of view. Now the question is, how about the eigenvalues? Because we are looking at the eigenvalue problem of, so if I know, let's say I have an L operator and it has some state lambda, which is its eigenstate, and it gives a lambda, and then we have a lambda state. I don't like it this way, so let me write psi. So it gives us eigenvalue lambda. Okay, so this is understood. Okay, and we have a simplest case in which we have the non-degenerate eigenvalues, which means corresponding to every eigenvalue there is a unique eigenstate. Okay, this is the simplest situation which we can have. Now the question which we ask is that how about the adjoint? How about the eigenvalue of the adjoint operator of L dagger? Okay, so let's try to calculate that. So that will be, because now what will happen is we will use the duality, because L is acting on psi and it is giving us lambda psi. Now using the duality, so what is going to happen is there we are going to get a bra state, and then L dagger is going to act on that. So this fellow, let me take it inside. So what's going to happen, this I'll first take it inside. So it is going to give us L psi, but in a bra state. Okay, but because we know in the bra states what's happening, when you take it outside it is going to get conjugated. So so this is going to be the, if you have eigenstate for your, if you have eigenvalues and eigenstates for your original operator, then for the adjoint operator the eigenvalues get simply conjugated. That's the relation between eigenvalues of an operator and its adjoint operator. Okay, which makes a lot of sense, because we know by now that the way operator and its adjoint are related, L acts on the ket space and gets eigenvalues, while as the L adjoint is the same operator with the difference that it acts on the bra space, and it will have the same eigenvalue, but it will get conjugated because it's acting on a bra space. So that this much is plausible mathematically and physically as well. Now the thing is this, now let's say if this L operator was a charge conjugation operator C, okay, which means, say, let's say C was it's a conjugation operator, which means if I act on a charge state, let's call that N. Okay, so it will give me some eigenvalue which is the charge of that state, okay, N, and then N. And if the C dagger it basically acts on the bra state, okay, and it gives me the conjugate, okay, and then definitely the bra state. Okay, which means the eigenvalue here will be, let's say it was some let's say we have talking about any particle and antiparticle. So this will have a charge lambda, or any electronic or positron proton charge. Then this charge is going to be the adjoint of that. That is going to be just a complex conjugate of that. Okay, let's say if it was E, then it will be in some sense minus E. But you may think E and minus E are both real, but you know we always represent these as unitary operators. So it will get first conjugated, and then that minus sign will come down, and then that eigenvalue will come down. That way you will have a correct sign of your charges coming out. Okay, so it was just to tell you, it was just to give you a sense of like as the way we have understood the duality, dual spaces, like as there's a ket space, there's a bra space at the level of vector spaces, or at the level of the wave functions. Similarly, at the level of the operators, there's a similar dual concept. There's a similar dual operator. The dual operator is the adjoint operator. Okay, and in quantum mechanics, so there's a first we have a different kinds of dual operators, adjoint operators, like as we have different transpositions, different kind of conjugation operations in physics, like as charge conjugation, time reversal, inversion. These are all antilinear conjugation operations. All of them are represented as some sort of a complex conjugation, but with the difference that they are operators. Okay, so they are not acting on numbers, they're acting on vectors. Okay, so but there are these adjoint operators. Then there's a special class called observables. For the observables, it is a necessary, I think I talked about that. Why is it necessary? that this one, the adjoint and the operator itself, they should be the same. Okay, so and we now understood that for a adjoint operator, we can see that the relation between eigenvalues of an operator and its adjoint is they are complex conjugate of each other. So now immediately, if you tell me now that I have a Hermitian, I think it becomes very clear why there are real eigenvalues. It's very clear from our relationship here. Let me get rid of these things. So now we can immediately see, if you have a Hermitian operator, we know that Hermitian operators have always real eigenvalues that can be immediately seen. So Hermitian operators, they always have real eigenvalues, which is also needed, because actually whenever we do an experiment, that also always gives us real values. So if we have to represent observables by any operator, it has to be such an operator such that the numbers which we get after calculation should be real. So now we can see that L, Hermitian operator is an operator such that L and H dagger are same. So therefore, if this is eigenvalue lambda, this is eigenvalue lambda conjugate, and they have to remain same. That's the only, this equation is only true for the real numbers. Real numbers are the ones which are their own conjugates, their own complex conjugates. Okay, so that's why this is a trivial kind of a consequence of or implication of the fact that for operators, if you have the eigenvalue lambda, and then for its adjoint operator, the eigenvalue is always lambda conjugate. And if they are same, if you have two operators such that they're self adjoint, then in that case the eigenvalues are always, for self adjoint operators, eigenvalues are always real. Okay, so now the interesting, before I pause for the discussion, I want to just one another immediate thing we want to do for these Hermitian operators. Let's say we have a Hermitian operator, and such that it has this eigenstate v1, and it is an eigenvalue, let's call it lambda 1, and then we have v1. Okay, then we have the state. Okay, then we have another state v2, and it acts on v2, and we have another eigenvalue lambda 2. Fine, and then we have this v2. Now let us see what happens if for these two cases. To understand that, let's do a bit of an calculation here. So let's multiply both sides with the u as another state. Okay, so what do we get here is, or in other words, let's do it in the following fashion. Let us try to do it this way. Let's try to multiply it with the same thing. Okay, so what that will give me, I'm sorry, just a minute, it's a bit messy. Let me start again. So I have an operator h which is acting on v1, and it's giving me lambda times v1. Fine. So now let me multiply it on both sides with the v1 again. Okay, which means I will have a v1 here again. Okay, so this gives me that v1 sandwiching this one is going to give me lambda times this particular number. Let's say we have not normalized them. Let's keep them like that. Okay, that's our lambda. Now, if we had if we have a same state, but it has a different kind of an eigenvalue. Let's say we have, let's do it this way. Let's say we have assume that we have, let's take it the same thing, but it's operating on this state. And in case it has a different, let's assume it has a different eigenvalue. If we have states which have different eigenvalues, so let's call it lambda 1, and this let's call it lambda 2. Okay, so in that case, yeah, it's better to keep it so that we don't confuse things. So lambda 1 and lambda 2. Okay, this will be lambda 2, and this will become v2. Fine. So in such a situation, what happens is that you will see that okay, so now let's do it following way. Let's try to show that if we have, let's say we are trying to look at a situation that if we have eigenstates which are corresponding to different eigenvalues. So corresponding to lambda 1, we will have an eigenstate, let's say v1. Okay, and corresponding to lambda 2, we will have eigenstate v2. Okay, and if that is the case, if we have a different eigenvalues, the states corresponding to them, how will they look like? Okay, so we are just trying to see that. Okay, just a minute, I would like to show a result here. Let's say I have this particular state, which is v1 and v1. Okay, and then if I have this particular state, uh, okay, just a minute, let me do it again, okay. So the purpose here is to see if we have these different eigenvalues with different eigenstates. Okay, let's say we have v1 and lambda 2, we have v2. So let's see what we can prove about them. First of all, h acts on v1. Okay, and it will surely give us lambda times v1. Okay, or lambda 1 times v1. Okay, then on the other side, we also want to this is the first step. First we want to do this thing, and then we can also basically sandwich it with the same state, so that we take care of the advantage of the normalization later on. So v1, and we will get a v1. Okay, now let us say for the same state, or in fact we can take it, we can make it different. We have h which is acting on v2, and then we have the v2, and then what we get is the lambda 2. Okay, and then we have v2 and v2. Fine. So let us try to because it's same operator which is acting on two different states, let's try to basically yeah, if we have to kind of prove this result, let's for a moment let me take this v1 and v1 so that I can basically cancel these guys out. So I will have, let's now subtract it here. So because it's a very arbitrary case, we do not we are just trying to say that we have different eigenvalues. So if that is the case, okay, so v1 is a state which has two different eigenvalues, then this part, when we subtract, we are going to get lambda 1 minus lambda 2, and then we are also, it is going to get multiplied by v1 and v1. Okay, this is, I'm not going to take it 1, I'm going to take it some finite number. So let's say, so we are proposing that we have a same eigenstate, it has different, let's say, eigenvalues. If that is the case, okay, if we have such a situation, or in general, this is not true that we will have the same eigenstate, we will have surely different eigenstates. But this is to prove that if we have, if the eigenstates, if the eigenvalues are same, which basically means v1 and v1 are, this is like same state, then that way it's already proved that if we have same eigenstates, this is going to get 0, this is anyways finite. However, if lambda 1 and lambda 2 is not equal to each other, which means then that this particular state over here, the states which we will have, which if we do not have, if lambda 1 and lambda 2 is not same, then what it will mean that the states corresponding to lambda 1, and now we can also we will have another state which, because it's now different, we have taken them to be different, so we can write them as v2, v1 and v2. In that case, this is not going to be 0, it's only this particular quantity which is going to get 0, which basically means this particular number has to vanish. So which means if we have two states v1 and v2, they have to vanish, which means their dot product has to vanish, which means that they are orthogonal states. Okay, so this is another property of the Hermitian operators, that if you have these Hermitian operators and you have two different eigenvalues, the states which correspond to different eigenvalues, they are always orthogonal, and later on we can orthonormalize them, we can normalize them also. So that way what we get is an orthonormal basis, and I think this is really important property of it. And so we will get an orthonormal basis. So what we have said here is that if you have these Hermitian operators, then their eigen bases, or the set of all their eigenvectors, provide a basis for representing your wave functions, because it's by definition it becomes orthonormal, and we always seek the orthonormal basis to represent our wave functions, operators, and other things. So and this is one of the very important, this is another reason why we use Hermitian operator. Another advantage of using Hermitian operators is that Hermitian operators provide us with the Hermitian operators provide us with with a very important basis, which is automatically orthogonal by itself, but it can be always normalized. There's a process, something called a Gram-Schmidt ortho normalization, so that can be always used to get the orthonormal basis. So it gives us these orthonormal bases. Okay, these orthonormal bases, this is not any orthonormal basis. This is a very special basis. Let us give it a name also. So this is a basis made up of eigen vectors of the operator. Okay, this is the eigen basis of these operators. And why is it important? The immediate property of the eigenbasis is that, let's say if I have Hamiltonian and I have chosen the eigenbasis of it as my orthonormal basis. So what will be the advantage? The advantage will be that the Hamiltonian will immediately become diagonal. And what else do I want than to have my Hamiltonian in the diagonal form, because then I can read off its eigenvalues. Okay, so it is always, so in quantum mechanics, this is another important thing. In quantum mechanics, we need to use always we need to use some basis. So basis is always something which we use. And what kind of basis we are going to use in quantum mechanics is the eigenbasis of these Hermitian operators. Like, say if we are dealing with angular momentum, we will use the angular momentum eigenbasis. If you are dealing with a Hermitian Hamiltonian, we will basically try to get onto the eigenbasis of the the Hamiltonian operator. And why do we need that? Why do we need it? To represent the wave functions, the general wave function of our quantum system. Or maybe you want to make tensor products, you want to make it, write down a new wave functions for a more complicated or a many body systems. You can always start with some basic wave function, take a tensor product, but that basis itself should be a Hermitian, it should be an eigenbasis, because if it's an eigenbasis of only even a one part of the Hamiltonian, it means that you already have diagonalized that part of the Hamiltonian. You have to just doing some other perturbation theory or some other method, you have to diagonalize the other piece of it. Okay, so therefore this is to be noticed that we always use eigenbasis of the Hermitian operators in quantum mechanics. We always seek their eigenbasis and then we use it to represent any general wave function of our quantum system. Okay, that's another property. So that's why I was saying, so this is very important, that when we do something called spectral decomposition, we always use eigenfunction expansion. It's called eigenfunction expansion. And Fourier series is one of the examples of eigenfunction expansion. And where do we, what other examples do we have for eigenfunction expansion? You would all these expansions, like as you use Hermite polynomials, you use Legendre polynomials, you use Leguer polynomials, you use Bessel functions. All of them are eigenfunction expansions, because they are, all of them are basically the eigenfunctions of some differential operators, okay, which arise in specific, like as if you have a spherical symmetry, then Legendre functions will arise. If you have some cylindrical symmetry, you will have Bessel functions arising. Similarly, for harmonic oscillators with a very interesting quadratic Hamiltonian and a potential, you will have the Hermite polynomials arising as eigenfunctions. So Hermite polynomials are the eigenfunctions of the harmonic oscillator. Okay, so then you represent your harmonic oscillator, general wave function of the harmonic oscillator is then represented in terms of Hermite polynomial. Similarly, if you have a particle on a ring, if you have any periodic boundary condition, then you will always try to represent your wave function in terms of your Fourier series, in terms of sines and cosines. Okay, so that you will always, in fact, the way because in quantum mechanics the problem is to diagonalize your Hamiltonian. It's always that's the thing which we do, and one part of it is to find a suitable basis, because last time I said diagonalization is switching to a basis. So when you want to get, how do we calculate the eigenvalues? First of all, what's diagonalization? Diagonalization is a process in which you get the eigenvalues. Okay, you get your eigenvalues of your operator. And how do we get that? You convert it, you do transformations to that particular basis. Okay, we call them, I had given a name for them, we call them as normal coordinates. You have to go to those normal coordinates And when you get to the normal coordinates, then your operator automatically becomes diagonalized. Okay, so which basically means if I start with H, you have to do a set of transformations such that H becomes H diagonal. Okay, so this is a diagonalization procedure, that you multiply it, we do some sort of, actually those operations are rotations. You do rotations of your operator, you do rotations of the bases of in which you would have an original basis. You keep on rotating that basis such that you get to the diagonal form, and diagonal basis is that basis which is the eigen basis of that particular operator. So when you so the diagonalization is a basically an operation or the procedure to go from any arbitrary basis to the eigen basis. Once you go to the eigen basis, your operator all automatically gets diagonalized. Okay, that's why, so we always seek the eigenbasis. Even if we do not have an eigenbasis for a full system, part of a system, we start from there and keep on looking for the eigenbasis for the whole system. And it's all about so in other words, we can say that studying doing quantum mechanics is about also about looking for these eigenfunction expansions, because if you just know eigenvalues and eigen spectrum of your quantum system, so you know about one system. But if you know the eigenfunctions, then you can use those eigenfunctions to describe many other things. Like as if you know Landau problem, which is a very important problem in quantum Hall effect. But even there, you will see we use Hermite functions in a very modified form. But we get started. We try to basically map Landau problem, which is a two-dimensional free electrons in 2 dimensions. Then you apply magnetic field on them. This is the Landau problem. Then you have to solve the Schrodinger equation for such a system. But you map it, the way we solve it is that we map it to a harmonic oscillator problem. Then it will not become exactly the harmonic oscillator with some modifications, but then we use Hermite polynomials to solve even the Landau problem. Okay, so I think so that's what we do. So in some sense, the solution which was done by Landau of Landau problem itself was mapping or finding the right set of eigenfunction expansion for the Landau problem. Once we have those eigenfunctions, that's what we did. And same thing was done by later on by Robert Laughlin when he studied the same Landau problem, but with the interaction is present in the system, which is called a fractional quantum Hall. So he also did a similar technique, and then he wrote down a wave function by using these eigenfunction expansions for a very, very complicated situation, which is called fractional quantum Hall system. Okay, so that's why the Hermitian operators, they are really, really important, because earlier I talked about why from a physical point of view they are important to understand for closed quantum systems. And then they are important because they give us real eigenvalues. They also, more importantly, they also give us the eigenfunction expansions, which is really, really important. Okay, now I think we have more or less come to a close of our session. So I just wanted to, one other piece which I wanted to discuss basically was about if you have simultaneous, because you don't, whenever we study quantum system, we don't deal with only one operator. We have a set of operators, like as in angular momentum, we have Jz, and we have a J square operator, or we have Jx, Jy, and Jz. And then we want to solve the eigenvalue problem for all of them, Jx, Jy, and Jz. So typically you will have a set of operators, and then you want to solve a simultaneous eigenvalue problem for all of them. And or in other words, your quantum system is not completely described by a one single operator, by Hamiltonian alone. There may be other operators, or Hamiltonian itself may be depending on other operators. It may be commuting or non-commuting with other operators. So so the main problem which we want to solve is, given the set of, we call them completely complete set of commuting operators, CSCO. Given the CSCO, how do we solve the eigenvalue problem of them, and what do we know about that problem? I think that is something which we cannot talk about today. Let's take it further in the next session. And last thing which I wanted to say, I think we have been, this is our, I don't remember, this is our 12th or maybe 13th lecture today. And the idea was to have in this particular first basic course, we wanted to get a basic know-how, make ourselves at a very basic level compatible with the terminology, with the formalism of quantum mechanics, so that we can take it to the next level maybe in a separate course. And therefore, what we are going to do, we are in some sense coming to a close of our course. So there are definitely few more topics which we want to cover before we close. But do make your suggestions. If you have any suggestions, what do you want to cover more? We have certain special topics. Then there will be projects also which we want to do with some of the students, whosoever is interested. But do make your suggestions about the topics which you want to cover in the upcoming lectures. But I think we have whatever essentials of what this in this course we wanted to cover is the essentials of the quantum mechanics, without which it is not possible to make progress. Okay, so I think I will stop here. We'll take the discussion next time in the next session. Let me see if there are some any quick questions which I can answer now.